Hi guys, in this video we're going to be taking a look at graphing a simpler rational function. And so let's go ahead and just start by saying that these rational functions often have asymptotes, both vertical and horizontal, and those are going to be the key to graphing any of these graphs, is to first find what our vertical asymptotes are and then follow up by finding our horizontal asymptotes. So I am going to start with this idea of a vertical asymptote, which are these x values on a graph at which our function is undefined. And so one thing we want to keep in mind is that when we're looking at rational functions, the only way that we get a fraction or a ratio to be undefined is when we divide by 0. So what we know is that our vertical asymptotes occur where the denominator polynomial equals 0, assuming that this is our denominator polynomial. So when we look up here at our denominator here, I suppose that our vertical asymptote is going to occur wherever x plus 2 equals 0. So let's set it equal to 0 and solve for x here. But what we learn is at x equals negative 2, we would have an undefined value. So our vertical asymptote, first of all, is at x equals negative 2. And so what I'm going to do is I'm also going to go over to my graph here, and one of the first things I like to do is put the asymptotes on the grid. So we'll throw our asymptote on here. We say that x equals negative 2 to label this. Now looking at horizontal asymptotes have to deal with how the degree of the top polynomial compares to the degree of the bottom polynomial when you're looking at rational functions. In the event that the degrees are equal or the same thing here, we know that the horizontal asymptote must occur at the ratio of our leading coefficients. That is to say, the ratio of our top leading coefficient over our bottom leading coefficient. So in this case, since the leading coefficient on the top is negative 2 and the leading coefficient on the bottom is 1, we can determine that our horizontal asymptote must occur at this horizontal line, y equals negative 2. And so I'm also going to go put this on my graph over here and make sure we label it. Once, however, I get both of my totes that exist for this graph, what we're going to do is we're going to find 2 points to the left of and to the right of this vertical asymptote here. Now one thing I want to do is I'm going to throw in an arbitrary graph here and say that this could very well be what our graph looks like, but for what it's worth, what we know about our graph is it's pretty boring out here on the outsides because it's just going to keep getting close to this horizontal asymptote. And it's also pretty boring as we get close to this vertical asymptote because our y values are either going to increase without bound or decrease without bound. So where is our graph really interesting at? I would argue that it is interesting just to the left of and just to the right of every vertical asymptote. And so our method, of course, is to let's table some values here to the left and to the right of every asymptote. And you'll notice that I always ask for 2 points to the left of each vertical asymptote and to the right of each vertical asymptote. So what we're going to do is, somewhere here, we're going to build a table of values. And so we'll say x are my inputs, y or f of x are my outputs here. And we're going to pick the 2x values that lie to the left of my vertical asymptote. So that would be negative 4 and negative 3. Excuse me. And then 2 to the right, which would be negative 1 and 0. So we do always want to use 2 x values to the left of and to the right of every vertical asymptote. But from here we're just going to go plug these into our function. Now the neat thing about having a rational function is that you know that each one of your answers has to be a ratio or a fraction, where we're going to get some value on the tops and some value on the bottoms independently. And so we're going to say, let's assume I'm going to plug in these numbers here. Then I'm going to assume that we'll just plug them into all the tops first. This makes your work a little bit more efficient if we just do all the top values first. So looking at the top rule here, we have negative 2x is our value on the top. So if I were to plug in negative 4, I'd have negative 2 times negative 4. It would look like this here, but essentially I know that I would get a positive 8 on top. In terms of negative 3, we would have negative 2 times negative 3. I know that I get a 6. If I plug in a negative 1, I get negative 2 times negative 1 is a 2. And then 0, an easy one to plug in, we say negative 2 times 0 is just 0. So after running through and getting all of our numerator values, let's go back through and now obtain our denominator values with the same inputs. Except for this says take your x value or your input and add 2 to them. So negative 4 plus 2, of course, I would say negative 4 plus 2. See, this is me showing my work here, negative 2. But we could just say, you know what, I know that negative 4 plus 2 is negative 2. You wouldn't necessarily have to show that. Negative 3 plus 2 would give us a negative 1. Negative 1 plus 2 would give us a positive 1. And then 0 plus 2 would give us a 2. Well, I always say that once you get your rational value here, or your fraction, then we'll go back and change any of these that we need to a decimal. So I notice that 8 divided by negative 2 is a negative 4. I'm going to box that. I get a negative 6 here. I'll box it. Get a positive 2 here and box it. And 0 divided by anything non-zero is 0. So with these ordered pairs that we've determined here, we're just basically going to go put these onto our graph. And so we would say that negative 4 and negative 4 is on my graph. So from the origin, I'm going to go left 4 and down 4, and I'll draw my ordered pair in here. I notice that I go left 3 and down 6 from the origin. So 1, 2, 3 left, 1, 2, 3, 4, 5, 6 down. And we can clearly see that then this branch is going to lie down below our horizontal asymptote here and approach negative infinity as we approach this vertical asymptote from the left. So we can go ahead and put in our branch of our graph here. You have to mind my handwriting here. But let's go ahead and plot our 2 points to the right of the asymptote. We say negative 1, positive 2, so we'll go left 1 up 2. And then 0, 0 happens to be a point on the right side of the asymptote. So we know that as we approach this vertical asymptote from the right side, these values must be going up. And as we go further and further to the right here, we would just be getting closer and closer to our horizontal asymptote. So this would be our graph here. The only other things we want to determine are what were these 2 points left and right, which we did. We're just going to fill them out. And then also write our domain of range as intervals. So the 2 points to the left, we had negative 4, negative 4, and negative 3, negative 6. On the right side, we had negative 1, comma 2, and then we had 0, comma 0. So with respect to our domain, the neat thing about this is once we knew these two asymptotic values here, we could have stated the domain because our domain here is always going to be all the x values except for those where we're undefined. So in this instance, I'm going to say it's negative infinity up to negative 2, but we shouldn't include negative 2. And we should start just to the right of negative 2 and go to the right here. So we're going to say in union with negative 2 to infinity. Essentially, whenever you've got your vertical asymptote value, then we can say that our domain is all the intervals that do not contain negative 2 here. When we look at our range, same thing with our range, our graph hits every single y value on the y-axis, except for it only gets close to negative 2, it never quite gets to negative 2 here. So with respect to our range, we're going to say that it's negative infinity up to negative 2 here, all the way up to here. And then it starts on the other side of negative 2 and goes up forever and ever. We say negative 2 to infinity. Okay? So making these graphs, here's the rules. Always find your vertical asymptotes first, which are the zeros of the denominator. And then find your horizontal asymptote by, if it's even, or sorry, balanced degrees on top and bottom, it'll be the ratio of your leading coefficients on top and bottom. But once you get those asymptotes on, we're always going to plug in two x values to the left of and to the right of every vertical asymptote, and then graph it from there, determine our domain of range. Cheers.